Good day, students. In this clip, we're going to be going over an example on how to solve optimization and mathematical modeling problem. All right, so these are the steps that we're going to execute in carrying out the problem solving process. Step number one, we're going to create a model of the situation that involves using a well-labeled diagram to create an optimization function. It can also be referred to as the main or primary function, and a constraint or secondary function. You could have more than one constraint on an optimization function. All right. After creating the model and the constraints, we're going to do the substitution here. In this case, we're going to isolate a variable from the constraint functions and then plug them into the function to be optimized. That enables us to differentiate the optimization function in terms of just one variable as opposed to multiple variables, all right? And after we create that new function in terms of just one variable, we're going to state the constraints, the domain constraints in that one independent variable that we have. And then after that, we're going to find the potential extremas, and we know what the potential extremas are. They are the critical points. And if the situation involves endpoints, maybe our domain is a closed interval, then the endpoints are also candidates for a potential extrema. All right, so we're going to find all of them. And then part 4, we're going to classify our extremas. So we're going to either use the first derivative test or the concavity test to determine where there are critical points or the max or the min, and then we can also evaluate the endpoints to see if they are max or minimums, all right? And then lastly, we just state what our solutions mean. All right, so let's go ahead and take a look at the first example. All right, so it says a box with an open top is made by cutting small equal squares from the corners of a 8 by 8 inch sheet of steel and bending the sides, bending up the sides. So how large should the squares cut from the side be to create a box with maximum volume? So in this problem, we are going to be maximizing the volume. All right. Okay, so let's go ahead and do the parts. Part number 1. We're going to start by creating a model. Okay. All right, let's see if we can create a diagram of the situation and represent it using mathematical tools. All right. So let's see, we have a sheet of steel that's square boxes, equal squares are cut from the sides. All right, so let's say we have this sheet of steel right here. It's a different one. All right, so let's say we have the sheet. This is the sheet of steel, and we know what the dimensions of the sides are. It's 8 by 8, so the side is going to be 8 inches. It's 8 inches, and then this side right here is also going to be 8 inches, so it's 8 by 8. All right, and then in order to create an open top box, we are to cut boxes, squares from the sides. All right, so let's create um, a representation of that cut on the sheet of steel we have. So let's just cut this box out of here. Equal boxes are cut from all the corners, okay? So let's just cut out squares of equal size, congruent squares from all 4 sides like this. All right, so it's then folded to create a box, okay? So let's say that, let's call the sides that we cut out, let's call it X. So this is X, and this is X, since they're all equal squares, this is X, and this is X. All right, so in order to create a box, all you just do is you're basically going to fold it, okay? So you can basically perforate, soften this area right here, just soften it up a little bit, soften this area up, and then this area. soften this area up, and then you're going to just fold the sides, and then you're going to have a square. Okay, so let's make a sketch of what the box is going to look like. Okay, so have a box right here. So we're just gonna bend it. All right, so you see this piece right here, you just bend it upwards, bend it, bend it. That this is not perfect, it's just a sketch. And that one goes down from here, steps over here. Just over here. All right, and then we'll have a box looking something like this. All right, so you basically have a square like this. So let's label the sides. So this side right here is X, and then this is X, and then that's X right there. So all we just did is we just folded the sides to create this box right here. Okay. All right. So now what we're going to do is we're going to create mathematical models. So the first one we want to deal with is the optimization or the primary function. Okay. So let's write that down. So what on earth are we optimizing? So let's write down the name first. Optimization function. You can call it the primary function too if you want. So optimization function, let's look at the problem. We're asked to determine the square cuts that will create the maximum what? The maximum volume. So we are optimizing or maximizing the volume in this case, all right? So what is the volume here of this shape? We know what the formula for volume is, right? If this is the length, let's call this the length, and then this is the width, and this right here is the height. So what is the volume of a box, an open top box? The volume is length times width times height. All right, so that's the optimization function. But we don't have an infinite number of resources. There are constraints on how much material we have, and that's defined by the dimensions of the sheet. So let's now take a look at our constraint function. So constraint. Now there we have constraint functions because there are constraints on the length, the width, and the height. Okay, so constraint functions in this case. All right, now what constraints are there? Well, there's a constraint on how wide this can be. So what is the length? What is the length of our box? Now the length of our box, we know the entire length is 8. So if you take out an x from, if you take out an x from 8, and then take out another x from 8, what is left as the length of the box is going to be this portion right here is going to be 8 minus 2x. So that's the constraint on our length. All right, so first constraint, length is equal to 8 minus 2x. All right, now how about the constraint on our width? Can you see what the constraint on the width is? It's exactly the same as the constraint on your so remember we started with a square sheet, so this entire thing is 8. So what we're doing is we're taking out length x from the sides. That will determine the over here. That will determine the width of our box. So we take an x out of there and an x out of there, and then what do you have left as the width from here to here? You just basically take out the two x's. Let me use a ruler to indicate that measure. So this side I have left here is going to be 8 minus 2x also. All right, so that will be your width. So the width, another constraint on the width is 8 minus 2x. And then lastly is the height. What is the height of this box? Now imagine folding the edges of the box. If you fold the edges, this side and this side will come together to form this side right here. This side and this side will fold together to form this side and this side will form that side, and then this side will be this side together. So basically this length right here will unite together to form the height. Okay, so the height basically of our box is given by x. Okay, so there we go. So this is our model. We have a diagram, and then we have four equations, four functions that we're going to unite together to solve the problem. All right, let's move on to part two. Part two is where we're going to be doing some substitution and the determination of our domain. All right, so part two, we're going to substitute um, portions of our constraint into the optimization function so that we can express this function in terms of just one variable. All right, so the question is, what variable do we want to use in our optimization function? We can use only one variable. If you notice, the length, width, and height are all described in terms of x, so that looks like a perfect variable that we can use. We can use other variables, but this is much more convenient. Okay, so remember, for your substitution, you want to end up with a function in only one variable. So we're going to express this as v of x equals the length is x times the width, which is 8 minus 2x, times the height, which is uh, 8 minus 2x also. All right, so just substituting these constraint functions into the optimization function, we have this nice function right here. Okay, now if we expand this, we just FOIL it out, we end up with v of x equals 4x to the 4x to the third minus 12x squared plus 64. Okay, just by distributing, this is what you get. Now we have to state the domain. Okay, we have to state the domain here. So let's state the domain for x. So if you look at the figure, go back to the figure, we're gonna, this function is in terms of x, so the domain is going to be the constraints on x. So how small can this box be? This box can actually become a point, basically. So you just have a flat sheet of steel, you decide not to cut anything out. So in that case, what would the value of x be? If x is just a point, what would the width be? In that case, x would be 0. All right, so the smallest that x can be is 0. In that case, you're not cutting out any box. So the lower bound in our domain for x is going to be 0. So x could be 0. Now, how big can x be? We know that we don't have infinite number of material. Infinite size of material here is constrained to 8 by 8. So how big of a box can we cut out from every side of the 8 by 8 square? So to see the maximum cut we can have here, we can just look at the midpoint. I'm going to sketch the midpoint right in a minute. All right, so that basically, see this line basically shows you the biggest boxes or squares you can cut from the side, okay? So this entire thing is x, 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 x. You have 4 big boxes cut from the side. So what you're going to have basically is just one infinitely long, one really long line, okay? So, or yeah, and then the area enclosed in within will be nothing basically, all right? So if you want to break it up like this, how big can x be? If the entire thing is 8 units long and you want to cut out the x in such a way that they meet at the center, the length of x is basically going to be 8 divided by 2 because you have one x on this side and then you have another x on this side. All right, we're talking about the maximum value of x because you're going to cut it from each side. So what is the biggest value of x that ensures that they have equal split and the entire length is 8? You just simply divide 8 by 2, right? So that's 4. That's the biggest value of x, so that you can cut out a x by x squared from 4 sides of the 8 by 8 sheet. Okay? So our upper constraint on the x is 4. All right, so now we have the domain, and we also have the function in terms of one variable. Now we're going to shift our attention to part 3. We're going to find the extremas. Find the extremas. All right, so basically we're going to be looking for the potential ones, okay? So potential extremas. And then to find the potential extremas, we are going to be looking at the critical points and critical points and endpoints. Remember, those are our potential extremas. Why are we looking at endpoints here? Because you notice that our domain is a closed interval, so those ones are going to be candidates for consideration in the maximum value. All right, so let's start off by finding the critical points first. So let's find the critical points. What on earth are your critical points? Those are the points where the derivative, where f prime is equal to 0 or dne. In this case, we're going to be looking at v prime. All right, so v prime is what we're going to be looking at. All right, now since we have the function, we're just going to differentiate it once. So we're going to go, let's rewrite v of x. V of x is equal to 4x to the third minus 12x squared plus 64. And then v prime of x is going to be 12x squared minus, okay, I made a slight mistake in my expansion. Just make a real quick correction here. This is supposed to be 32. Sorry about that. And this right here is 32 also. Okay, so it's 32x squared, and then this is 32x squared also. So now when we take the derivative of this, it's going to become 64, and there's also an x here. It becomes plus 64x plus, and then when we differentiate this, it equals to 64. Okay, so that's the derivative. Sorry about the mistake. Okay, now we have the derivative. We're going to solve for where it's equal to 0 or where it does not exist. So for v prime equals 0, so 12x squared minus 64x plus 64 equals 0. And then to do this, you notice that we can divide everything by 4. If we divide by 4, we end up with 3x squared minus 16x plus 16 equals 0. And then we can factor this into x minus 4 times 3x minus 4 equals 0. And then when we solve this, we have x is equal to 4 thirds and 4. Okay? And then this is the first critical point. When is v prime, when is it non-existent? When does it not exist? If you examine this function, this is a quadratic, it's a parabola, and we know it doesn't have any corner cusps, vertical tangent, and doesn't have any discontinuity. So when is v prime non-existent? Never. It is differentiable in the entire domain. Okay. Now one thing you'll notice is that the one of the critical points happens to intersect with one of the endpoints. So that's kind of nice. So these are our critical points. And then where are our endpoints at? Our endpoints are going to be, and then x equals 0 and 4 are our endpoints. So we have 4 twice, so we can just check it once. So these are the candidates. These are our potential extrema. Okay? So what we're going to do, we're looking for the maximum. So let's shift our attention to part 4. We want to classify them. Classify. So what we want to do in this problem, it says maximize. So in this case, we want to find the max. The nice thing about this is we don't have to use much calculus. We can just plug this candidate into the original function, and the biggest will be our maximum. Okay. So to do this, we're going to test test all of them. V of 4 thirds. We're going to plug that into the original function. We know that the original function v of x was, when we broke it down, it was 4x to the third minus 32x plus 64. So v of 4/3 is simply what you get when you plug in 4/3 into the function. 4/3 to the third minus 32 times 4/3 square plus 64 times, so next here also, 64 times 4/3. And then when you plug that into your calculator, you have 1024 over 27. All right, and then the next one we're going to check is v of 0. V of 0, you have 4 times 0 to the third minus 32 times 0 squared plus 64 times 0. And you can clearly see that this is 0. And then v of 4, you see this 4 right here is an endpoint and is also a critical point. So we're doing 2 in 1, okay? Just do it once. So 4 times 4 to the third minus 32 times 4 squared plus 64 times 4. And if you plug that into your calculator, you will get 0 also. Okay, so what does this tell us? We can clearly see that the maximum happens at x equals 4/3. Okay. Now, if you have a maximum at a point, what is the concavity at that point? Let me make a sketch for you. So if you have a maximum at this point, that means that it's going to be higher than every other neighborhood point, right? So what's the concavity around this point? The concavity is downwards. So we can use the concavity test to determine if this is in fact a maximum. Although we already know it's a maximum because it's the biggest out of all of them. But let's just use the concavity test to verify. All right, so what I'm going to do is basically evaluate the second derivative at 4/3. If it is concave down or negative, then, if it's negative, sorry, that means the function is concave down. That confirms that this point is a maximum, okay? So we're going to use the second derivative test. Second derivative, you can call it second derivative or concavity test, okay? Second derivative or concavity test. All right, so v prime of x was 12x squared minus 64, x plus 64. So v double prime, second derivative of that, is simply going to be 24x minus 64. Okay, so what is v double prime at 4/3? What is the concavity at that point? If it's negative, if it's negative, then the concavity will be downwards, which means it's a max. Okay, so let's evaluate it. So you have 24 times 4/3 minus 64. You do the calculations. 3 goes here, 1, 3 goes here. 8 times 4 is 32 minus 64. The second derivative is negative. Is a negative. So that means that this implies that v is concave down at x equals 4/3. So if it's concave down, that gives us confidence that we have a maximum at that point. Okay, so the maximum volume is at x equals 4/3. That's where it's at. Okay, all right, the last piece, part 5, we're going to write our conclusion. Okay, conclusion. All right, so the conclusion, the question asked us for how large should the square cuts be to create a box with maximum volume. So let's see what the dimensions of a square cuts should be. The dimensions of the square cuts that generate the maximum volume. What's the maximum volume? The maximum volume is the value of v at 4/3, and we already calculated what that was with a calculator. It's the maximum volume of 1024 over 27. So the maximum volume of 1024 over 27 cubic inches is 4/3 inch by 4/3 inches. So if we cut out a 4/3 inch by a 4/3 inch from all 4 sides, Then we are going to have a open box that has the maximum volume of 1024 over 27. And this is approximately 37.9 inches, but that's good enough. All right, so that's that. But thanks so much for taking the time to watch this presentation. You can always feel free to subscribe to my channel for more updates. Please post a comment to let me know what you think about this clip. And do give me a thumbs up if you like it. I appreciate it. More clips can be found on myself.com/calculus. Thanks again for watching and have a wonderful day.